What time is it exactly? If you glance at a clock on the wall, you're watching light reflected from its surface. That light takes time to reach your eyes. Your optic nerve takes additional time to transmit the signal. Your brain then spends roughly tens of milliseconds assembling those signals into what you experience as reality. By the time you perceive the now, it has already passed. You are always unavoidably experiencing the past. As a species, we have spent centuries trying to overcome this. We organize civilization itself, financial markets, navigation systems, communication networks around increasingly precise definitions of the second. We demand synchronization. Yet, here is the uncomfortable truth. We have never built a perfect clock. Not because we lacked ingenuity, not because we failed to invest enough effort, but because, according to our best understanding of physics, a perfect clock cannot exist. To measure time with absolute precision would require pushing the laws of the universe beyond their limits. Today, we are going to try anyway. We will attempt to build the ultimate timekeeper step by step, and at every stage, reality itself will push back. At its most basic level, a clock needs one thing: an oscillator. An oscillator is any system that repeats its motion with a regular rhythm. In the 17th century, Galileo Galilei identified the first great timekeeping oscillator, the pendulum. He observed that a swinging lamp in a cathedral completed each swing in nearly the same amount of time, regardless of how wide the arc was. For small angles, the period of pendulum, the time for one full swing, is given by this elegant equation. T is approximately 2 pi square root of L over G. Let's break that down carefully. T is the period, the exact time it takes for the pendulum to swing all the way out and all the way back. 2 pi, this is just a geometric constant because the swing traces part of a circle. G, this is gravity. Since the pull of Earth is roughly constant, we can't really change this. That leaves just one variable we can control: L, the length of the pendulum arm. Notice what does not appear in this equation: mass. It doesn't matter if the weight at the bottom is a feather or a brick. The timing depends almost entirely on how long the rod is. The implication was intoxicating. Build a pendulum of the exact right length and you could tame time itself. And for a while, it worked. Air resistance drained energy. Engineers compensated this with gears and escapements. Heat was even more insidious. As temperature changes, materials expand and contract. When the pendulum rod lengthens, L increases, so the time T gets longer. The clock slows down. When it gets cold, the rod shrinks and the clock speeds up. Seasonal temperature swings alone could introduce errors of minutes per month. Ingenious solution followed. Composite rods, mercury pendulums, exotic alloys, but they all fought the same underlying problem. Matter is never perfectly stable. It bends, it expands, it ages. So, we abandoned swinging objects entirely. If solid matter could not keep time, perhaps vibrations could. Quartz possesses a peculiar property known as the piezoelectric effect. Apply mechanical stress and it generates electrical charge. Apply an electric field and it vibrates. Carve it into tiny tuning forks, a crystal quartz oscillate at an extremely stable frequency. In most digital devices, that frequency is 32,768 vibrations per second, exactly 2 raised to the power 15. Electronics divide the signal repeatedly until a single pulse remains. 1 second. Quartz clock transformed timekeeping. They were compact, affordable, and orders of magnitude more stable than pendulums. But quartz is still a physical matter. Over years, its internal lattice shifts, alters its behavior. These changes are tiny but relentless. The result is drift, typically seconds per month. For a wristwatch, this is acceptable. But for a satellite navigation, it is disastrous. An error of a microseconds translates into kilometers of positional uncertainty. To build a clock that would not age, we need something fundamentally different. Not a manufactured object, but something defined by nature itself. An atom. Every cesium-133 atom is identical to every other. It does not wear out. It does not deform. Within each atom, the electrons and nucleus occupy discrete energy states. When exposed to radiations at a specific frequency, the atom transitions between two closely related energy levels, known as hyperfine states. This transition acts as a natural, perfect oscillator. It is the purest, most stable rhythm the universe offers. The atomic clock works by bathing a cloud of cesium atoms in microwave radiation. We fine-tune that radiation until the atom absorbs the energy and jump states. It's like tuning a radio dial until static revolves into perfectly clear signal. For cesium-133, this clear signal frequency is exactly 9,192,631,770 cycles per second. That number is so stable, it officially defines the second. Modern atomic clocks are astonishingly precise, deviating by less than a second over many millions of years. For a moment, it seemed we had reached the end of story. But precision comes at a cost. To read the atom, we must interact with it, and interaction inevitably disturbs the system being measured. Early atomic clocks worked by launching atoms through a vacuum chamber, a design known as a beam clock. Their motion introduced unwanted Doppler shifts, a smearing of the signal due to atoms' speed. More fundamentally, quantum physics imposes unavoidable limits. This is the Heisenberg uncertainty principle. Simply put, increasing the precision of your measurement increases the uncertainty elsewhere in the system. Measurement creates noise. To suppress that noise, we did something extreme. We essentially froze time for the atoms. Using laser cooling, a technique often called optical molasses, we reduced atomic motion to near absolute zero. We then employed atomic fountain clocks. These tossed the supercooled atoms upward, letting gravity momentarily hold them at their apex, effectively stretching the measurement interval by watching the atoms fall. Accuracy improved again, and once again, physics pushed back. Einstein revealed that time is not absolute. Gravity curves space-time. The stronger the gravitational field, the more slowly time flows. This is not a philosophical speculation, it is experimentally verified. In 2010, researchers at NIST, National Institute of Standards and Technology, demonstrated that two atomic clocks separated vertically by just 33 centimeters tick at measurably different rates. Your head ages faster than your feet. The consequences are profound. A clock on a mountain runs faster than one at sea level. A clock in orbit runs at a different rate than one on Earth. But gravity is only half the story. Velocity affects time as well. According to Einstein's theory of special relativity, a clock in motion ticks more slowly than one at rest. The faster an object moves through space, the more slowly it moves through time. This effect is not theoretical, it has been measured repeatedly. Atomic clocks flown on airplane return measurably out of sync with identical clocks left on the ground. Particles created on Earth's upper atmosphere should decay in microseconds, but because they travel near the speed of light, their internal clocks run slowly, allowing them to reach the surface. Motion itself distorts time. This is why GPS satellites must account for both effects simultaneously. Their speed causes onboard clocks to lose about 7 microseconds per day, while weaker gravity causes them to gain about 45. Only by correcting for both does the system remain accurate. Time is shaped by gravity, time is shaped by motion. There is no single flow that all observers share. So let us narrow the ambition. Forget universal time. Suppose we only want to measure time perfectly here, in this exact spot. Even then, we encounter the final boundary. To understand why, we have to look at what a clock actually does. A clock separates the past from the future. It creates information. Tick, tock, tick, tock, tick, tock. But in thermodynamics, creating information, creating order requires energy. Every tick has a cost. As we try to slice time into smaller and smaller bits to get more precision, we must make our clocks tick faster. To tick faster, the clock needs more energy. If you want to measure a millisecond, you need a battery. If you want to measure an attosecond, which is 10 raised to power minus 18 second, you need a laser. The relationship is brutal. Higher precision requires higher energy density. Now, recall Einstein's most famous equation. E equals mc squared. Energy and mass are equivalent. As we pump more energy into our ultimate clock to make it more precise, we are effectively increasing its mass. Eventually, you reach a terrifying limit. To measure an interval known as Planck's time, which is 5.39 times 10 raised to the power minus 44 seconds, you would need to concentrate so much energy into such a small space that the energy itself would collapse under its own gravity. You would create a black hole. This is not a metaphor, it is a prediction of quantum gravity. The moment you build a clock capable of perfect precision, its density becomes infinite. It creates an event horizon, a wall around reality from which nothing, not even light, can escape. The clock would vanish from the observable universe. It would cease to transmit information. The universe prevents us from measuring time perfectly, by destroying the clock that attempts to do so. So, at every scale, we encountered a limit. Pendulums failed because matter responds to heat. Quartz failed because matter evolves. Atoms fail because measurement alters reality. Synchronization failed because time is relative. And finally, ultimate precision failed because knowledge requires energy, and too much energy breaks the fabric of space-time. There is no perfect clock. Time is not a single river carrying everything forward together. It is local, contextual, and guarded by the laws of physics. We have built clocks precise enough to navigate space, coordinate global networks, and probe the deepest structure of reality. That will have to be sufficient. Perfect time was never offered. The universe keeps it for itself.